Welcome to G Fun Facts Online. When you look up at the clear night sky, you might see the Milky Way as a serene, luminous river of stars. For centuries, that's how humanity saw it. But this placid surface hides a tumultuous reality. Beneath this starry river lie unseen ripples, vast, wave-like oscillations of stars and gas that betray a violent and epic history. These ripples are the ghostly echoes of colossal cosmic collisions, and they are the key to unlocking our galaxy's deepest secrets. Today, we're diving into this river of stars to explore the unseen ripples of the Milky Way, a story of galactic archaeology that is rewriting our understanding of our place in the universe. This is the story of how we learned our galaxy is still ringing like a bell from ancient impacts. The field that unearths this cosmic past is known as galactic archaeology. Just like terrestrial archaeologists excavate layers of Earth to understand past civilizations, galactic archaeologists dissect the components of our galaxy to piece together its history. Every single star holds clues. Its chemical composition, its motion through space, and its age all tell a story. Low-mass stars are particularly important. They are true cosmic fossils. They have lived for billions of years, and their atmospheres contain a pristine record of the environment in which they were born. By studying these ancient stars, astronomers can reconstruct the timeline of events that shaped the Milky Way. The traditional model of our galaxy is a neat one. It has several distinct parts: a dense central bulge of old stars, a flat, thin disk, where most stars like our Sun in active star formation reside, a thicker, more diffuse thick disk of older stars, and a vast spherical stellar halo containing ancient stars and globular clusters. For a long time, how these components formed was a subject of debate. But modern cosmology, supported by massive astronomical surveys, favors what's called the hierarchical model of galaxy formation. This model suggests that large galaxies like the Milky Way grew by absorbing or eating smaller ones over cosmic time. This process of galactic cannibalism is a fundamental part of how the universe is built. When a large galaxy's gravity tears apart a smaller companion, the victim isn't immediately erased. Its stars are stretched and dispersed into long, faint arcs known as stellar streams. These streams, like ghostly trails, continue to orbit within the larger galaxy for billions of years, preserving the memory of the long-dead galaxy. Early evidence for this violent past came from ground-based telescopes like the Sloan Digital Sky Survey. But it was the European Space Agency's Gaia mission that truly started a revolution. Launched in 2013, the Gaia spacecraft has been on a mission to create the most precise three-dimensional map of the Milky Way ever attempted. Its primary job is astrometry, the precise measurement of the positions, distances, and motions of stars. Gaia's accuracy is almost unbelievable. It can measure a star's position to the equivalent of the width of a human hair, viewed from 1,000 kilometers away. It does this using two key techniques: stellar parallax and proper motion. Stellar parallax is the slight shift in a star's apparent position as we view it from different points in Earth's orbit around the Sun. By measuring this tiny angle, astronomers can calculate a star's distance with unprecedented accuracy. Proper motion is the star's movement across the sky over time. Gaia's repeated observations of over 1 billion stars let it track these tiny movements. But Gaia goes further. Its radial velocity spectrometer measures a star's speed towards or away from us. This is done by observing the Doppler shift in the star's light. Light from a star moving toward us is shifted to shorter, bluer wavelengths, while light from a receding star is shifted to longer, redder ones. Combining parallax for distance, proper motion for movement across the sky, and radial velocity for movement towards or away from us gives us a complete 6D map of a star's position and velocity in space. The Gaia data releases have been landmark events in astronomy. Gaia Data Release 2 in 2018, for instance, was hailed as a complete step change in our understanding of the universe. With this wealth of data, astronomers could finally watch the collective dance of the stars, and it was in this intricate dance that the unseen ripples of the Milky Way were finally brought to light. Gaia's precision allowed astronomers to identify the culprits behind these ripples, a series of cataclysmic collisions with smaller galaxies. Two events stand out for their profound impact. The first was the last great merger in our galaxy's history. It happened about 8 to 11 billion years ago, when a dwarf galaxy, now known as Gaia-Sausage-Enceladus, or GSE, slammed into a much younger Milky Way. The name is a composite from two teams who discovered it. Gaia-Sausage comes from the sausage-like shape of the population of its stars when you plot their velocities. Gaia-Enceladus was chosen because, like the mythological giant Enceladus who was buried under Mount Etna, the remnants of this galaxy were buried deep in the Gaia data and have shaken the Milky Way ever since. At the time of the collision, the GSE galaxy was about 10% of the Milky Way's mass, making it a truly significant event. The evidence is written in the stars. Gaia revealed a huge population of stars in the inner halo moving in highly elongated or sausage-shaped orbits. These orbits are completely distinct from the nearly circular orbits of stars born in the disk. These stars also have a unique chemical signature. They are generally poorer in heavy elements or metals than disk stars, but their pattern of elemental abundances is different from other halo stars, pointing to an extragalactic origin. This merger was a violent event that fundamentally reshaped our galaxy. The collision heated the pre-existing thin disk of stars, puffing it up and scattering its stars into the more extended thick disk we see today. The GSE also brought a substantial amount of gas with it, which fueled a massive burst of star formation, creating another part of the thick disk. The debris from the GSE, including at least 8 large globular clusters of stars, now makes up a large fraction of the Milky Way's interstellar halo. While the GSE merger was a single, transformative event in the distant past, the interaction with the Sagittarius dwarf galaxy is a more recent and ongoing affair. The Sagittarius dwarf is a small, loop-shaped galaxy that is currently being torn apart by the Milky Way's immense gravity. Over the past 6 billion years, it has repeatedly punched through the disk of our galaxy, leaving a series of ever-widening ripples in its wake, just like a stone dropped into a pond. Astronomers have identified at least 3 major collisions, occurring approximately 5.7, 1.9, and 1 billion years ago. Each of these passages has had a significant impact. The gravitational disturbance creates ripples of gas and dust. These ripples lead to localized increases in the density of interstellar material, which then collapse under their own gravity to form new stars. Incredibly, the first major collision with Sagittarius, around 5 to 6 billion years ago, coincides with the formation of our own Sun, which is about 4.6 billion years old. While it's impossible to say for certain that this collision directly triggered the collapse of the specific gas cloud that formed our solar system, it is a truly tantalizing possibility. The ongoing disruption of the Sagittarius dwarf has also created one of the most spectacular sights in our galactic neighborhood, the Sagittarius Stream. This is a long, looping trail of stars that wraps entirely around our galaxy, a breathtaking testament to the relentless power of galactic tides. The study of this stream and the ripples it has induced is the foundation of an exciting new field, galactic seismology. Just as geologists study seismic waves from earthquakes to understand the Earth's interior, astronomers are now using these stellar ripples to probe the structure and dynamics of our galaxy, including its most enigmatic component, the dark matter halo. These galactic quakes are triggered by the gravitational pull of satellite galaxies, like Sagittarius. As the dwarf galaxy passes through the disk, it creates a disturbance that propagates outwards, causing stars and gas to oscillate up and down. By studying the properties of these oscillations, their amplitude, their wavelength, and their speed, astronomers can infer the properties of the medium they are traveling through, which is the galactic disk, embedded in its dark matter halo. Dark matter is the mysterious, invisible substance that is thought to make up about 85% of the matter in the universe. It doesn't interact with light, but its gravitational influence is profound, shaping the structure of entire galaxies. The Milky Way is thought to be embedded in a vast, roughly spherical halo of this dark matter. The way the ripples propagate is extremely sensitive to the gravitational potential of this halo. By analyzing the detailed motions of stars within the ripples, astronomers can create a motion picture of the galactic disk's warp and wobble. This, in turn, allows them to map the shape and mass of the dark matter halo. For example, recent studies using a special type of star called a Cepheid variable to trace the galaxy's warp have suggested our dark matter halo is not perfectly spherical, but slightly oblate, like a squashed sphere. Stellar streams, the tidal debris of disrupted galaxies, provide another powerful tool. The exact path and shape of these streams are exquisitely sensitive to the gravitational field they orbit in. If a stream passes near a clump of dark matter, that clump will leave a gravitational imprint, creating a gap or a wiggle in the stream's otherwise smooth structure. By identifying these perturbations, astronomers can map the distribution of dark matter substructures. This technique is so powerful, it can even help us test different theories about what dark matter is made of. For example, models like cold dark matter predict a different level of clumpiness on small scales than models like fuzzy dark matter, and these differences should leave unique signatures in stellar streams. The Gaia mission has been a spectacular success, but it is far from the final word. Its data will be analyzed for decades, but the future of galactic archaeology lies with a new generation of telescopes. The Vera C. Rubin Observatory, currently being built in Chile, is set to revolutionize time-domain astronomy. Its Legacy Survey of Space and Time, or LSST, will repeatedly image the entire southern sky for a decade, creating a massive time-lapse video of the cosmos. It will detect billions of stars, allowing for the discovery of fainter and more distant stellar streams, providing a more complete map of the Milky Way's merger history. The Rubin Observatory could potentially triple the number of known dwarf galaxies orbiting our own, giving us more targets to study. Then there's NASA's Nancy Grace Roman Space Telescope, slated to launch in the late 2020s. Roman will have a field of view 200 times larger than Hubble's and will observe in infrared light. This will allow it to peer through the dense clouds of dust that obscure our view of the galactic center, revealing the structure and history of the inner galaxy in unprecedented detail. It will also study the halos of nearby galaxies, providing context for our own galaxy's formation. These missions will be complemented by others, like the James Webb Space Telescope, which is already providing stunning insights, and spectroscopic surveys like Foremost, which will provide detailed chemical abundances and velocities from millions of stars, helping us to trace them back to their specific merger origins. The discovery of the Milky Way's unseen ripples has fundamentally changed our perception of our galactic home. The serene river of stars is, in reality, a roiling, dynamic entity, still sloshing from the impacts of ancient collisions. These ripples are a powerful tool for understanding our galaxy's violent past, its hidden architecture, and the invisible scaffolding of dark matter that holds it all together. As we stand on the cusp of a new era of astronomical discovery, we are poised to unravel the epic story of the Milky Way's formation in even greater detail. The ghostly streams of devoured galaxies and the subtle oscillations of stars are the clues that will guide us, reminding us that the universe is not a static canvas, but a dynamic and evolving masterpiece. We are just beginning to appreciate its true beauty and complexity.